Okay, welcome. We are going to look at the next circuit type, which is called a combination circuit. And this one, it's called a combination because there's elements of it being in series and then elements of it being in parallel. And what do I mean by kind of elements of it being in series? I would say that electricity, as it's traveling, is forced to go through a component, and it doesn't have the choice to take a different path or to avoid a certain obstacle or resistor or component, whatever it is. Okay, so let's kind of look and think about electricity, say, flowing out this way. Okay, and when it gets to resistor 1, there is no choice but to go through resistor 1, right? And that's a property of a series circuit, is that when electricity hits a resistor, an obstacle, it has to go through it. So it continues on, goes through that, but at this point right here, we actually have a choice. Electricity gets to branch, and it can choose to go this way. Okay, and as it goes this way, right, it again hits a resistor and doesn't have a choice, but it did have a choice to take that branch or that branch, right? Once it continues or chooses this branch, it is kind of stuck going through both of these components. Which is kind of like being in a series circuit, kind of going through both of them in that path. Okay, let's just refer to, in orange there, I'll put a B1 for kind of branch 1. And if the electricity does not choose branch 1, you know, where it had the ability to choose, it may have gone this way. And so we can refer to that as branch 2. In which case, whichever branch the electrons chose to follow, right here they meet back up and finish the loop heading back to the battery. Okay, it'd be really good for you to draw the circuit, draw the table, so now's a good time to hit pause and get yourself organized. Okay, so the first thing I'm going to do is calculate the total resistance. And even just looking at the chart that kind of organized what was given, you can see that I only have one voltage, and these voltages are not all equal because this is not just a straight parallel circuit. So I can't just start filling in tens. I don't have any current right now, so the only thing that makes sense that I'm probably going to be able to figure out is the total resistance. Okay, well, total resistance in a series circuit, okay, if you remember, is simply the sum of all the resistors. The total resistance in a parallel circuit is this 1 divided by the sum of the reciprocals. Okay? So what I'm going to do is I'm going to follow the path of electricity, and I'm going to think about, am I in a part of the circuit where I have series, in which case I should simply be adding up the resistor value, or am I at a section where I have branching, in essence a parallel circuit, where I really should be using this formula to calculate the resistance of that section of the circuit. So as the electricity starts heading out this way, I hit the resistor, R1, and I have to go through it, right? So that's like series. I'm going to have R1 plus whatever other resistance I meet. But the next thing I get to is that branch, that choice, right? And so we said once we have a parallel circuit, it should follow this. So I'm going to write 1 over, and then here I need the reciprocals of the resistors. Well, in this branch, it's not quite that simple. I don't have a single resistor, I have 2. Okay, so I really need the resistance of this branch. Well, the resistance of branch 1, right, is really just, those are in series, would really just be the sum of those 2 resistors. Oh, that was supposed to be a 2. And 30 and 80 is 110. Okay, so think of kind of combining these into one total resistance along this, taking this branch as 110 ohms. So I have the 110 on one branch. The other branch has a total resistance of just the one component, 50 ohms. Okay, and I don't have any more reciprocals or fractions here because I have no other branches. Each branch creates one of these fractions. Okay, it's 1 over the resistance of the branch. After these branches merge back together, there are no more components here. If there were, then I would put plus, okay, outside of this fraction, plus, and then just the resistance of that component, kind of like I did with the 100. So that's our formula. I'm going to say RT is equal to that 100 plus then 1 over 110 plus 1 over 50. All right, I'm going to tell you that you're just going to want to use a calculator to go figure this out. All right, if you've got a simple calculator, you might need to record decimals along the way, right? What is 1 divided by 110? Make it a decimal. What's 1 divided by 50? That one should be easy, it's 0.02. Add those together, right? Then do 1 divided by that number. Okay, it just so happens that when I did this, I got, let's see, 0.02900909 repeating. Okay, like that. When I divided that, I got 34.375. And my 100 had to add to that, so I ended up with 134.375 ohms. All right, now I'm filling in things in the chart just so I can keep track of what I've got. I'm going to kind of round that for the sake of my chart. So I'm going to say 134. Okay. All right. Looking at the chart helps me to see if I can use Ohm's law. We can always use Ohm's law if we're talking about all the totals or if we're talking at a very specific spot along our circuit. So I now have the total voltage and I have the total resistance of my circuit. So it makes sense to go ahead and the next thing, so let's see, this was kind of the very first thing I did was finding total resistance. So we're going to say the very second thing I'm going to do is to use Ohm's law to calculate the total current flow through this circuit. So we had a voltage of 10 volts. I'm not sure how much current we have yet, but I do know I have 134, and I'm going to use that value if I'm calculating, 0.375 ohms. So I need to do, right, I would divide both sides by the 134, so it's really 10 divided by 134.375, and let me pull out my calculator. I don't have all this calculated ahead of time. 34.375. I got 0.0744. It keeps on going, but I'm gonna stop there. It rounds, does not round up, and that's current, so that's amps. I'm using red in my table just so it's a little easier to kind of spot. So that's 0.0744. Now, we're talking pretty small numbers here, so if I round to just 0.07, since we're already talking such small numbers, that's a fairly significant difference, so I don't want to be too quick to do that. Okay, so the next thing that I can do is, let's kind of label that point. Normally we might put a little symbol here to kind of represent the total current flow. Okay, so the total current is heading out here. And remember that this first resistor, all of the current had to go through it. We hadn't branched yet. So I know here that I1 is the full amount of current of 0.0744. Just kind of by looking at my schematic, I can understand that. So I get to go ahead and fill in that the current at resistor 1 is also 0.0744. Now I don't get to do that with the others because we have this branch where that current is going to start to divide and split up, and some of it's going to choose to go one way and some of it's going to choose to go the other. How it's going to choose is really more flow will go through the path of less resistance. So we should at the end see this path with only 50 ohms of resistance get more of the flow, more of that 0.07, than that will choose to take this path that has 110 ohms of resistance. Okay? But because I knew that, you could kind of state that, that's maybe something I did, is that I knew that I1 was going to be equal to IT. Okay? But figuring that out unlocks Ohm's law at the first component. So I can say that the voltage drop at the first resistor is equal to the current through the first resistor times the resistance. So I get V1 is equal to 0.0744 times 100. And that's going to move my decimal 2 places, so I'm going to get 7.44 volts. Okay? Now, the next thing we know is that the voltage in a parallel circuit, each branch kind of gets the full voltage of a circuit normally. Now this is not a true parallel, right? But it's parallel from here on. So while we've got a voltage drop of that 7.44, whatever voltage is left at that point, kind of the pressure, each branch is going to get. So let's write it out this way. I'm kind of on my fifth thing, if you will, just trying to keep track of the order in which I flowed through this problem for you. So let's write out that the total voltage has to equal the voltage at the first component, okay, plus the voltage of the branch. So that could be branch 1 or it could be branch 2. Okay, and so those voltages have to be the same. Now we will get a voltage drop, that kind of divides those here in the first branch because there's 2 components, but we can at least determine what that amount is that's going to get split up. We've got 10 volts total. We found a voltage drop at the first resistor of 7.44. So if we find the difference between, just subtract 7.44 from both sides, we know that the voltage drop along the branches is going to be 2.56 volts, and that'll be the same here. Now, in the second branch, there's only one component. So that one component will get the full voltage drop. So I could say that V4 here is the 2.56, and I'll fill that in on my table. Okay. Now, the table really helps me because I see that I now know the voltage, okay, or the voltage drop at resistor 4. I know the resistance of resistor 4, so it must be that I can calculate the amount of current going through resistor 4. And that helps me because remember that 0.0744 is going to split up. Some of it is going to take this path through 2 and 3, where these, kind of highlight, these are going to have to be the same. Once the current chooses that branch, it's the same electricity going through resistor 2 and resistor 3. But I just don't know how much chose that branch versus what chose that branch. So we can figure that out because of Ohm's law. So the sixth thing I can find out, I'm going to say V4 is equal to I4 times R4. So we've got the 2.56 volts is equal to the current times our 50 ohms. So I really just need to divide both sides by 50, right? So the current is going to be the 2.56 divided by the 50, which is what? 2.56 divided by 50, 0.0512. That's amps. So some people may write that as 51.2 milliamps. I'm going to leave it as amps, and we'll fill that in. 0.0512. Okay. Now, remember, we said that we had a total current, right, that was bigger, and that total current, right, has to equal the amount of current that took branch 1 and the amount of current that took branch 2. Well, we know the total current is the 0.0744, and we just found out that we had 0.0512 amps take branch 2. So knowing those two things, I can figure out how much took branch 1. So just subtract the 0.0512 from both sides. And what are we going to get? Let's see, I guess we're going to get 232.0. So 0.0232. Alright, and again, that's the same for both. Now that we have the currents going through each resistor, resistor 2 and resistor 3, right? I already knew the resistances. I can use Ohm's law. So let's see, that was the 7th thing I did, and kind of the 8th and 9th thing is going to be using Ohm's law. So V2, so this is 8th step, is equal to I2 times R2, and then you could say the 9th step will be doing V3 is equal to I3 times R3. Alright, so again, the voltage is the unknown, but the current is 0.232, and the resistance of resistor 2 is 30. Down here, we've got the same amount of current in that branch, 0.232, and we had a resistor of 80. So I just need to multiply 0.0232 times 30, and I'm going to get 0.696 volts. And then here I'm going to multiply the same current by 80 this time, and I'm going to get 1.856. Now if I add these two together, 1.856 plus the 0.696, I should get, okay, the same voltage here, 2.56. I knew that the voltage of these two, okay, they have to add to equal that. Each branch gets the same voltage. Okay, so I have 0.696 and 1.856. There you go. So I know that's a lot, but if you can do your best to have, gone back and kind of retrace the steps and try to follow it and make sense of that. This is really, I'd say, for our purposes, a little harder than what you'd see on a quiz or test or anything, but it'll give you kind of push you to just be challenged a little bit. So if you can understand this, then I think anything that we might throw at you that's simpler should be just even easier to handle. All right, good job.